In the 1720s, the greatest minds in math, including Daniel Bernoulli, encountered a difficult mathematical problem.
How do you interpolate the factorial sequence with a continuous function?
You can't just draw any polynomial. It has to perfectly satisfy a continuous version of n factorial equals n times n minus 1 factorial. No one knew how to do it. Multivariable calculus didn't exist. There was no gamma function yet.
But Leonhard Euler found a clever mathematical method.
Using this exact integral, and nothing more than single-variable calculus, he created a continuous bridge between whole numbers and the infinite. That means he extended the factorial function from discrete integers to all real numbers.
Here is his original, incredibly clever trick. Euler started with this specific integral, which we now call the beta function. To make it easier to evaluate, he assumed the second exponent, y minus 1, was an integer.
Let's redefine it as the variable n.
Since y minus 1 is now n, the argument y naturally becomes n plus 1. His goal? To expand this integral using a standard technique, integration by parts.
First, let's bring up the integration by parts formula.
We set u equals 1 minus t to the n, and dv equals t to the x minus 1 dt. Watch what happens to the boundaries. If we plug in t equals 1, the 1 minus t part becomes a flat 0. If we plug in t equals 0, the t to the x part becomes 0. This works as long as x is strictly positive in order to avoid division by 0. The entire boundary term just vanishes entirely. This leaves us with just the second half of the formula. We can pull out the constants n and x from the integral. Notice the mathematical relationship here. The power of 1 minus t went down by exactly 1, and the power of t went up by 1. Euler found a recurrence relation. The integral can be expressed in terms of itself. Euler realized he could just repeat this process infinitely. Each time he applies integration by parts, it introduces another fractional factor, n over x, then n minus 1 over x plus 1, all the way until the power of 1 minus t completely reaches 0. And what is left is a simple integral that is easy to evaluate. Evaluating that base case just gives us 1 over x plus n. Combining all of Euler's fractions, we get a beautiful, pure algebraic formula. The numerator is exactly n factorial. Now here is the key algebraic step. Look at the denominator. It resembles a factorial, but it lacks the first few terms.
If we assume x is an integer, say m, Euler just multiplied the top and bottom by m minus 1 factorial.
The denominator absorbs these terms, becoming exactly m plus n factorial. Since the modern gamma function is essentially just a shifted factorial, where gamma of k equals k minus 1 factorial, Euler's formula aligns perfectly with this definition. This completely proves the exact relationship between the beta function and gamma function for integers. To generalize this to all real numbers, Euler did something extremely clever. He rearranged the equation to solve for m minus 1 factorial. He then investigated what happens when n approaches infinity.
That fraction expands cleanly to n plus 1 times n plus 2 up to n plus m.
Notice that if we factor out an n from each of the m terms, we get n to the power of m times a sequence of fractions. Since n approaches infinity while m is fixed, those term over n vanish to 0. So, for enormous values of n, this entire fraction behaves asymptotically like just n to the m. Substitute that asymptotic behavior back into the original limit, and we have our factorial. Euler then simply replaced the integer m with a continuous variable x. He expanded the beta integral using the algebraic fraction we derived. And that is how Euler connected the discrete factorial to a continuous function. If you enjoyed this proof, subscribe to Matilda Academy. See you next time!